Right, so I do have all your exams that we will pass back, but we'll go through the lecture portion first, and then we'll get these out. I'll give you advance under learning materials for test 1. I do have my solutions guide, so I worked through the test too, so you can see my work. I'll post that Thursday. I still have a couple people that are still doing a makeup due to illness, so they're coming in Thursday. So after Thursday, I'll make this available to you. So you'll get them tonight. Go ahead and try to do your best to get through it. There's a few that took the makeup tonight. I'll get those graded, but I've got to do that. So that's there. And then we'll pass them back, and we'll see where we go. Overall, it was greater than 50% pass, or over 70%. With the homework being, I think it's about 10%. What you can figure that getting all the homework done, and especially if you can get that extra credit. And when I extend it, that gives that extra 20. So you should be getting like 105% on the homework. That gives you an extra 10.5%. So it's, when you're done with things. But that should be enough to boost whatever test averages you have by 1 grade. So if you average a C, it should get you a B. If you average a D, that should still get you to a C. If you average a B, get you into an A, and I'm sorry I can't do too much. It might get you into the A pluses. So, a lower A average can get boosted up there. A pluses are a little bit harder because they want 97%, right? And I do look at things. There's no formalized things with the coordinators as far as what we do, but since the final exam you will be comprehensive, so we'll test you on everything. I can look at the questions that cover this stuff, and I can see if there's improvement. I do look at. So regardless of where you're at, you'll just keep making forward progress, making improvement, and I will reflect it in that final grade because I do a holistic look at things. So yes, whatever's in the syllabus, the number-wise, that's a minimum, but I do reserve the right to say, hey, the student made some good progress. Numbers say this, but the progress says this, and so I can go up a grade or half a grade or whatever needs to be done. Okay, so keep going, and we'll get you there. All right, and the grades are posted, right? So you should know what you've got. You'll see why it is, and I am a math teacher. That doesn't mean I'm really good at arithmetic, especially when I'm grading exams. Someone came in, I was off by 10 points, so I had to, went from a 65 to a 75 just because I was adding in my head and in the middle of things. But you'll be able to catch those things. So check out the arithmetic, make sure everything's there. So that's why I'll also post my solutions. So sometimes, again, I'm just going through 100 of these, and sometimes I lose, but we'll make sure that we'll make it right. Okay. So this week we started, this is Tuesday. Thursday we started on 11.3, which was the product rule and the quotient rule. So it was kind of how to take a derivative when we've got two things that are either being multiplied or divided. What we're going to look at tonight is something called the chain rule. And it's a chain rule because we're looking at things that are compositions of functions. So there's going to be a function inside of a function. And we'll go through the PowerPoint somewhat, but I'm going to start off with sort of a different more of a direct technique of what we're doing. Okay, so we use the chain rule whenever there's an inside of a function. So how do we know there's an inside function? What does that look like? What is the key mathematical symbol for inside versus the outside? Parentheses, yeah. There's some other things that kind of do it. So, but if we certainly see something with a parentheses, we'll see that there's a function inside, and then so there's an inside function. The outside function might be something as simple as something like this, an exponent. So what you're going to do is you're going to see that that's actually two functions. There's something inside the parentheses, and we do something to x, we do it, and then we raise it to the third power, which is sort of like another another function. So what I want to show you is I'll do something a little more simple. What if we had x to the fourth raised to the fifth? Now we can do this with the methods we have, right? We could do the algebra part first. So what would we do? X to the fourth raised to the fifth becomes what? If we do algebra. X to the 20th. We multiply exponents. So that's the key part. And now when we take its derivative, so if we want dx, right, we'll just do it that way, it's going to be 20 x to the what power? 19. What I'm going to do right now is show you how the chain rule would work with this thing. And then we'll kind of look at some of the slides, which are supposed to, it's their textbook's way of trying to make things clear. In my mind, it kind of makes it less clear. So that's what I'm trying to show you, the way that sort of is clear for me. And then hopefully it'll make what the textbook is doing easier to find. So I'm going to switch colors here. So what we do is well, at least this way I do it. If you're going to like work on something like a machine, where do you start? Do you start in the middle or do you start on the outside? Outside, because you can't get to little stuff in the inside, right? So that parentheses we can't quite get to yet. So what I would do is I would take the derivative of the outside. So this is just some function raised to the fifth power, right? So we could think of it as, and what they'll use another variable instead of x. They'll say this is u to the fifth power. So, but how do we take the derivative of something to the fifth power? Fifth power comes down, and we subtract 1 from it. Okay, so part of the chain rule is just going to be the inside stuff. It's not been touched yet, right? It's still x to the fourth, but we've got this 5 down here, and then we're going to have it to the fourth power now, right? And nothing happened to the inside. Okay, so we just dealt with the outside. But you're working on an engine. You take off the outside, now you can get to the inside, right? So let's think of, we dealt with the outside. So what would be the derivative of the inside? 4x to the third. And let's just see what would happen if we multiply these things, because that's the other question. Do we multiply them? Do we add them? Do we subtract them? Do we divide them? And let's see what happens. So 5x to the fourth. So 4 to the fourth is x to the 16th, right? 5 times 4 is 20, I'll put it that way, and I got my x to the third. Now if I got x to the 16th times x to the third, what do I do with the exponents there? That's when I add them, I get my 19. So this ends up being 20 x to the 19th. Okay, and that's what I got when I did it with sort of the algebra method. So I know since I got the same answer, sort of using that, when I do a chain rule thing, I take the derivative of the outside with the inside unchanged, because I can't get there yet, right? It's inside. Once I take care of taking off the bolts of the outside, I can now work with the inside, and what I end up doing is I just multiply the two together. Okay, so that's kind of how I looked at it. Those are just the rules of operation. Okay, derivative of the outside part first with the inside unchanged, and then take the derivative of the inside and multiply it by everything you did on the outside. And we end up with the right answer. So let's just see how that would work over here. So what am I going to get out of this? 3 comes down. I'm going to get 3. And I'll switch over to blue. I don't do anything to the inside yet. What do I do to the exponent? Subtract 1, because that's the derivative rule. And then what's the last thing I need to remember? Well, let's take a look now. I can get to this inside. What's the derivative of the inside function? Well, if f is 2x plus 4, its derivative would just be 2, right? Derivative of 4 is 0. Derivative of 2x is just 2. So then I just got to multiply by 2. Well, can I take 3 times 2? Yes. So my final answer is just going to be 6, 2x plus 4 squared. And we're going to leave it there. We don't have to do the algebra of foiling it out and stuff. And what you'll see is we use it a lot when as these get to be larger and larger exponents. You don't want to have to FOIL that out multiple times. So when we've got parentheses with something to an exponent, that's when we use the chain rule. Where's another time we're going to use the chain rule a lot? Square roots, which is really a 1/2 power, right? And now I put some funky function in there. See, I've got an inside and an outside. So that's what we're going to go through tonight, is looking the inside function, the outside function. The last thing is we'll apply it to a business application where it doesn't quite look that way. It looks like two separate functions, but one of the functions is like the production function, how many units can we produce? The other function might be the profit of, if I sell this many units, how much am I going to make? And so I can't sell more than I make, right? But if I sold everything I made, I could say, well, I'll make a profit if I can sell everything I can make. And typically, we're going to get there a little bit further. We look at a supply. We use the derivative in looking at supply and demand. So there's a function actually for the demand. At this price, this is the demand for the item, and at this price, this is the supply that we'd have. And when supply matches demand, that's the best situation, because you're making exactly what's being demanded, and so you're selling everything, and you're not having things in warehouses. You're also not being short of stuff where, hey, we could have sold another 100 if we had them, right? That's the perfect situation. So we'll look at things like that with calculus. Again, we'll be able to do that. Okay, so it kind of makes sense. So if you just think of it, if you can spot the inside and the outside, is just take the derivative of the outside and just sort of, whatever's in there just kind of goes along for the ride. And then I take that derivative of whatever's in there and multiply it by what I've got. That's all the chain rule is. And now let's see. They're going to introduce it, and it says, I think, too many words, but we'll walk through it. Okay, so yeah, lots of words. So what it comes to be is I want us to think of this function, 3x plus 1 on the inside, right? So we can see an inside here, raised to the 0.5 power, which is, what's another raise to write the 0.5 power?
Square root.
Good, square root. Or 1/2, right? So we could have been giving it this way. But what they want you to see is that if I gave you the number x, what would you do with x? Plug it in, and you would calculate from the inside. And then you would take the square root. So that's kind of their approach. Is they do it backwards how I do it. They go into the inside first and get that, and then they get the outside part, which to me is backwards how I like to think of it, because, again, you can get to the outside stuff because it's outside. The inside next. So anyway, but see, it's, this is a composition. It's a function inside of another function. So this is where they're going to kind of, so yeah, here's our inside function, here's our outside function. And they'll start using, what they'll do is they'll do a substitution. Instead of writing 3x plus 1, they'll just say this is another function. We'll call it u. Why not? And there's this, you didn't see this, but in the math department, there's this big thing about, because in calculus, they call it u substitution. But then they said, you don't always have to use u, so why should we call, anyway, I stayed out of it. I just said, we just call it u because that's what they do. So, so most textbooks will do something like this. So this is some function, right? 3x plus, we just give it another name. Again, once you get used to this, you don't go through all the steps. You don't call it u, you just say, hey, cover it up. It's that whole thing, and then do the outside stuff, and then do the inside stuff. That's how I do it. But let's kind of go through it. So if we call it something else, notice we can then sort of say there's stuff raised to the 1/2 power. We know how to do that. And what they do is now they talk about, okay, if I were going to plug something in, I put it in for the x first, so they're going to start from the inside and work outwards. That's okay. We'll see we'll get the same result. So they say h of 1, we put that in. 3 times 1 is 4. Well, 3 times 1 is 3, plus 1 is 4. So they do the math. And then the last step is you would take its square root, so you end up with 2. Right? But they're kind of getting us to think of what the arithmetic process is. And so the same thing is we put the one into the inner function first, we calculate it, and then we get the outer function. So they're kind of going from the inside out. That's kind of all they're, and again, it's a lot of smoke and mirrors, if you want to think of it. Okay. And then what they're going to do is now talk about this chain rule. Since we've got these two parts, how do we think about the derivative? What would the derivative of this thing be? And again, they just sort of simplify. Instead of calling it u of x, they just say, let's call it u. So then, but be careful how you use your letters here. It gets to be insulting to, anyway, we'll get past that. Why do they use these? Why not use G and something else? Anyway. Okay, so what they're going to get to is that when we take the derivative of this thing, we're going to take the derivative sort of, now notice that f is sort of our outside function, so they are taking the derivative of the outside function here, and then what are they doing? They're multiplying by the derivative of the inside function. But notice they're using two different notations, right? I would have said this is the derivative of f of u times the derivative of u. So that's another way we can think of it. So this is where I struggled because I like the prime notation better than the fraction note, the du dx. I had that, just the notation itself gave me problems. So either one of these will be true, but again, what we're going to do, we'll go through a few examples. Just think it's outside derivative, inside derivative, and multiply. Okay. So f of the quantity is the derivative of f elevated at that quantity times the derivative of the quantity. Okay, so take the derivative of the outside, multiply times the derivative of the inside. And again, since they're two separate pieces, you could do it in either order. You could take the derivative of the inside first if you wanted, and then multiply by the derivative of the outside. That's okay. But it's usually the outside you see first. So if u is u squared, again, what's that going to give us? The outside will give us 2u. Now, u could be something more than just a single letter. It's representing some other function. And then so du dx is the derivative of that whole inside stuff. So notice it's always, this u is sort of whatever's inside unchanged. So that's kind of the key with the chain rule. You'll always see whatever you're doing, you'll see the inside stuff stay there. It doesn't change. But then you'll see its derivative there. So you start to see those two pieces. Now remember, we are going towards the end of the class to be doing things backwards, which is called integration. So that's part of what I want you to see is as we get these derivatives, be able to spot the inside, the outside, and then the derivative of the inside, because that's going to be helpful down the road when we go to integrate something like that. We need all those pieces to put it all back together. Okay, so again, and this one, I don't know, it just kind of, yes, u to the third. Again, take the outside function, 3 comes down, so you get 3u to the 2, because you subtract 1. And then whatever's on the inside, we're going to multiply. Now, I didn't follow this step here, but they're just, okay, if we're going to take this as, maybe I think they're using the product rule, thinking of it as 3 things. So they're kind of going to the product rule and say, yeah, it works. And I said, okay. So there's all these examples. How many of you feel it seems you believe it now? You're a believer that if I take the derivative of the inside, multiply that derivative of the outside, that will work. Give me the right. Okay, that's all we need to do. A little bit of faith. So again, it's a little bit overkill for me. Too much writings and information. And all of this is basically saying in different forms, take the derivative of the outside times the derivative of the inside. Okay. Now, some of these when we just have functions like x squared and stuff, we may be able to do this with a product rule or do this with something else, but we're going to be looking at functions fairly soon where we can't do that, and that's going to be exponentials, because there's going to be the exponent may be a whole function, and logarithms, there may be a whole function there. We don't do trig functions, so that's kind of good, but when we get to those two, exponential and logarithms, and again, at those of you in finance, you'll see those type of applications quite a bit. Natural log and e to the because it's used a lot in finance. So again, there's this table here, but I wouldn't worry about trying to memorize it. It's just, it's just saying, okay, if we only had x, this is how it works. We've got, if x is there's some function in there, we do the same thing, but then just remember to take the derivative of the inside. It's kind of a summary of everything we've done. Again, and we got to be careful. We might have some negative exponents, right? We might have fractional exponents. So all those things are there. So let's just take a look at a few. And what I'll do is, let's go ahead and look at a couple of these without all the, they spend about 6 pages, and again, a lot of words. You have access to the slide deck, which you're welcome to pull them up and take a read. It was done by the textbook company, so I'm assuming that it matches pretty much what is in the textbook. But let's just see how I think we can do it in pretty much one line here. So this first one, what do we do to get the derivative of the outside? What happens to this 3? Bring it to the front. What do I do with the inside? Just leave it alone. You can't touch it yet. It's still inside, right? It's in the middle. Can't get to that camshaft until you take the whole thing apart. And then, what can I do to this exponent, because it's on the outside? Subtract 1 from it. Okay, so now that I've taken apart the outside, let's just say that, what do I do with the inside part? Just take its derivative. So what's the derivative of 2x squared? 4x to the 1. What's the derivative of x? Just 1. The x is gone. Remember, it's really x to the 0, but that's how it looks. We're done. Not so bad, huh? No, I wouldn't. It's too much work. The answer is them together, and you would probably just, so this, I just did it so you could see the two parts, right? Here's the inside unchanged, here's the derivative of the outside, this is the derivative of the inside, and again, what your answer would look like is 2x squared plus x squared times 4x plus 1. This whole thing is your answer. And just put it all in. Don't try to simplify, quote, simplify, because doesn't simplify very easily. I mean, it's easier than trying to cube it first, but there's no reason to when we get this. Also, I noticed in the when we had the quotient rule, you end up with the denominator squared. You don't actually have to square it out. I mean, if you do it, it'll still count it as correct, but just leave it as this stuff squared. Don't FOIL things out if you don't need to. Okay, so far we good? How about B? What do we do with this 100? Just plop it in front. x3 plus x, we didn't do anything, we just copying. And then what do I do with that exponent? Subtract 1 from it, so I get my 99. And again, you might think, okay, I'm done, but not quite. What do we have to do with the inside? Take its derivative, 3x squared plus 1. So that's why I want you, in fact, I think I did another extension on 11.1 and 11.2 because there's a few, I don't know if anyway. Make sure you get through that, because that's the main thing, is once you start to get taking derivatives of things with exponents, this becomes second nature. And that's really what we need, is that you're just going through and not making, oh, this is you and this part's that. If you can do the chain rule just kind of by saying, okay, here's, I like to just kind of put my hand there, cover it, do the outside part, and then cover up the outside part and do the inside part, right? And it's those two things multiplied. So that's B. And again, I think it spends like 2 pages going through of why this works, but what would we do with C? to the 0.5 or 1/2, which, decimals or fractions. And again, what we want to see is there's an outside function, right? So this is the outside part. Bring it down and subtract 1. And again, when we subtract 1 with a fraction, we do the 2/2. So we get 2, 3x plus 1 raised to the negative 1/2 power. And then what do? Inside, which is just going to be 3. Derivative of 3x plus 1 is just 3. 3x to the 0 if you want, but that's just 3.
Why is it 3?
Thank you, not 2, just a half. I don't know where the 2 came from. I don't like fractions, so I just make things up as I go. Yeah, so 1/2, thank you. So 1/2. Okay, now they may want, again, this probably is an acceptable answer to WebAssign. I say probably because it should be. But if you want to, you might say, oh, let's combine the numbers at least, and we'll do 3 times 1. So you get 3/2, 3x plus 1. It just looks a little nicer. And this, if you want, you could put this down in the denominator. But I think, again, because we're focusing on the chain rule, they'll probably take it. Let me put an or over here. Or we could do this as 3 to square root of 3x plus 1. So all these are correct. Okay, so just whatever practice you want to go, going back and forth between the 1/2 power. Sometimes, especially if you're a little nervous about doing the square roots and the half powers and the fractions, the more you do it, then it's not so bad. Usually what I find, I can't remember, a good friend of mine told me this, is we usually do things just enough to hate them. If we did them a little bit more, we might start to like them. But we do them enough so that we just get them done, but we don't do them enough sometimes because we didn't really like it. It wasn't fun the first time, so we don't do them enough till they become fun. So if we do them a little bit further, sometimes they actually become fun. And then we've got this absolute value. Let's skip the absolute value one. I don't think we have any with absolute value. And I can't remember. There's something about the absolute value, but I don't think if we ever get to it, we'll go into a thing, but these are what we're going to have. And we'll take a look at the homework just to make sure. So again, and all this stuff is doing everything. Notice they'll end up with what we had. They spend a whole page setting it up. And again, you have access to this if you want to read through it. But I just want to kind of go ahead. They set it up as a u substitution thing. So they're saying instead of having this function, that's really 3u squared. We did that, but we just did it here. And so in one step, we were able to write everything out. And the main thing, we just had to remember to take the derivative of the inside, so we get 4x plus 1. So we kind of just went directly here. So this is the original inside, this is the derivative of the inside, and then this 3 and this 2 are the remnants. Those are the derivative of the outside part, right? So we'll just delete that. And I think as you get going with this, it's actually easier. And actually, if you do it at the beginning, sometimes you want to do it, the definition, to gain deeper understanding. But what I have found is that we go to this well, where did you come from? It's like all these extra steps that are really not necessary, that actually get in the way of understanding. So just think outside, then take the inside derivative and multiply the two together. Okay. We don't really need to put in a separate substitute. We're just going to say whatever's inside is going to stay together because it's in a parentheses, and we go from there. Okay. So yeah, take the outside, then the inside. We just kind of went straight to it. What's this one? And then they do a second method. Again, I'll let you read through this, basically ending up with the same thing. And I think they're thinking this one is actually more of what we did. It's just Take the derivative of the outside, take the derivative of the inside, and multiply the two together. Get it much quicker. Here's the 1 to the 100th power, and again, a lot of words and setting it up and all that stuff, but in the end, exactly what we did. The 100 comes down front, subtract 1 from the exponent, we got that, and then multiply by the derivative of the inside. And leave it like that. We don't, there's nothing to simplify. So our answers are going to become more expanded, but again, we have, this is a rate of change, right? If we need to get some value out of here, we can plug it in a graphing calculator and get a value back, and we now have a function that will give us the rate. What was the original function? The original function was some kind of value. Maybe it was the profit. This is the rate of the profit, right? So whatever that is, we're getting a rate of something. So that's all we have to remember, is that when we have the derivative, that's how things are changing. So it's like the marginal. It's kind of telling us where we're going to that next one. Right? It doesn't give us a total. It just gives us, are we going to get more or are we going to get less? Rates of change, instantaneous rate of change. That's what it gives us. And then we can use it. Here's the square root. And again, they kind of do the same thing we already did. We put it as a 0.5. I did it as a 1/2, whatever you're more comfortable with. There's the 0.5. There's the negative 0.5 because you're subtracting 1. And then the inside is 3, so multiply. Pretty straightforward. And again, multiple ways to write it. They get 1.5. I got 3/2. So all of them are correct. So far, so good. What time is it? Yeah, we're almost there. I just want to look at one applied problem. Here's, in words, you could do this one if you want. But again, we're not going to look at absolute values. I don't think they really occur much in business applications. I haven't actually seen any application direct. It just deals with distance, this idea of distance. But in real world applications, I have not seen an application of absolute value. Okay. So this is one, there's one in the homework very similar to this. And so what they do is, instead of setting it up as one function, they've actually already got it as two functions, right? But notice, here's our profit function, which is based on the quantity, how many widgets we can sell. And there's another function that tells us, depending upon how many we make, this is how many we'll be able to sell. So it's kind of like a, I guess, is that a demand, or demand is how much they're demand, how much the people want to buy. So I kind of guess it gives us a demand. So we make this much, that's what will be demanded, or the amount we'll be able to sell, then we can plug it in there. You could also, instead of putting this Q, you could just put this all up there, right? The thing is that we're going both places. So in this sense, it's a little bit cleaner because there's two inputs where this function would go, right? But this is the inner function, and this is sort of the outer function. So what we do is we follow the same sort of procedure where we'll take the derivative of the outside function, right, with the inside unchanged. So what would this derivative be? 0.5 comes down, so what's 1,000 times 0.5? It's going to give us 500. Good. Times Q, and again, we could write all this stuff in there, but we'll just put the Q for now. Q unchanged. What happens to this exponent up here? It's now a negative 0.5, right, because we subtracted 1 from it. How about 5Q? We take its derivative, what do we get? Just 5. So we don't see, so that's the derivative of the profit function, the outside function. What would be the derivative of what's going to be the inside function? q prime. So this will be 20,000 into the 0 power, right? Minus 200 into the 1 power minus 3n squared. Okay. And now what does our chain rule say? It's the derivative of the outside times the derivative of the inside. So, and again, we'll go to the next page and they kind of spell it all out, but it's going to be p prime times q prime. And it's kind of, we knew that one was inside, one was outside. So that's just going to be 500. And what I'm going to do at this point, just because I think they do this with the final thing, I'm going to put what q actually is. 20,000 n minus 100 n squared minus n cubed. So that was the inside function. That to the negative 0.5. I guess I should switch back here. Okay, plus 5, right, because that's the outside. And then what do we need to multiply this whole thing by? The q prime. So it's going to be, again, I probably didn't give myself enough room. 20,000 minus 200 n minus 3 n squared. So see how it kind of works. And some of these ones, because there was these q that happened in 2 places, it's kind of nice to leave it, and they'll set it up. And the one in the homework is set up just like this. They'll give you a function up there. You want to take its derivative, take this derivative, multiply them. But at the end, the goal is, can we figure out the rate of the profit change just knowing how much we produced? Yes.
So why did you omit the q after the 5?
Because I took its derivative, right? So if it was 5q, but when you take the derivative of 5q, that's just 5. Okay, yeah. Because you got this q is just, while it is a function, it's also, we're thinking of it just as if it were it's just like an x. Okay. So yeah, so the first step is the outside function. Just think of that variable as an x. Take its derivative. Boom, that's the outside. That's the whole outside. So that was this part here. So that's going to be that. And then we're going to take that times the derivative of the inside. Is that? And there's only one problem like that. You'll see. I'll show you. And then, so they work through it. And again, a little bit more. But I just kind of show you. So they take the derivative of the outside times the derivative of the inside using the chain rule. Just using these quantities. So they did the same thing. Here's the derivative of the outside, 500q to the minus 0.5 plus 5, because that other q is really q to the 0. The derivative of the inside, same thing we got. And the final step is to put those two together. We're going to just multiply them. And, well, they want it at a particular value, so you could put it together. So they just plug in 20, get one value. And then what they do is they put it into the original. So notice this is the derivative function. They also put it into the original q function so that they could just get the inside, and they get this number. So what they're going to do is they're going to plug this into the derivative function. To this, so that q, that 352,000 or whatever it was, is going to go in there, 352, and then so that goes in there, and then they're going to multiply it I don't see them doing this, so that Oh, have to click a little. So that gives the plugging in the value of Q into the outside function. This is the derivative of the inside function. When we multiply those two, we get its derivative. I like to let's just put it all together like I did on the last one. To me, it made a lot more sense to do this, and then just go ahead and plug in 20 for n, calculate the whole thing. Okay, but again, you could do it either way. To me, this makes more sense because I can say, okay, outside function multiplied times the inside function. The way they did it in pieces, I tend to lose pieces as I go. So, but again, I gave you these to review so you can kind of see which one makes more sense. And again, it goes through units. So I think that's really all I had for tonight. Let me just stop that. I'm just going to show you real quickly a couple things in WebAssign, and then we'll get handing back the exams. Oh shoot. Maybe WebAssign's down. Yeah. Anyway, there is one in WebAssign where the inside function is a rational function, is a fraction. So you're going to need to use a chain rule. So only one of them. The rest are pretty straightforward of what we're doing. Okay, but there is one. There's not one with a product rule and a chain rule yet, but there is one where you're going to need to use a quotient rule. It's a pretty simple. It's a linear in the top and linear in the bottom, but when you get to it, the inside, when you take the derivative of the inside, you'll need to use the quotient rule. Thank you. The last problem was much like that one. So, any questions? Any requests? Okay, so here's how I do passing back 100 plus exams when some of us have names that last name has like 2 words, and so sometimes they get split. So this is done by order in Canvas. I've put them in this order, and I put them by number. So then all you have to do is figure out where your name is and what number's next to your name, to the left of your name. And if you'll just tell me the number, let me stop this. We don't need to record this part.